So we have seen a lot of positive results. So it seems that infinite number of infinite items, it is still countable, right? So it will be very amazing to find out that a certain set is uncountable. And then we are going to show this result. So this result is proven by this counter, a mathematician called Counter. So if you have time, you can go to Wikipedia and check for Counter. So Counter's idea that real number is uncountable is not accepted while he is alive. Okay, so he's like, so a strong mathematician says that, oh, you are crazy. You must be thinking something that is nonsense. So it is impossible, something like this. And then Counter really get crazy later. He went to for people who gone crazy, this asylum. Okay, and a very sad story. And then his result that this concept of uncountable thing. Yeah, because a very famous, a strong mathematician thinks that Counter is crazy, so Counter's results cannot be published in good places. So you understand, right? So so the influence of that strong mathematician is so strong. So Counter cannot get his things published. He needs to publish it secretly in some very small journals, and then even the title does not look like what he wants to prove. Okay, but he still get the result published. Okay, so today we are going to look at his result. Okay, so in particular, we want to show that. Okay, so we want to show that we are not going to show that the whole real number set is uncountable. We are going to show a subset from 0 to 1. So all the real numbers between 0 and 1 is uncountable. Now, because of this, then it means that the real number set must be uncountable. Does that make sense? Because if a subset is uncountable, then the superset must be uncountable. Okay? Okay? Because if the superset is countable, then the subset must be countable. And now we have the subset uncountable, so the superset, the larger one, has to be uncountable. Okay? So how do we prove this? So this is the proof. So the idea here is proved by contradiction. So we're going to prove it by contradiction. So let's get it. So how do we prove by contradiction? So we assume to the contrary that this 0, 1 is countable. Okay, then what will happen? So we hope to, after getting certain steps, that we arrive at the contradiction. So what will happen? If 0, 1 is countable, then what? Then what? What is meant? So if it is countable, what do we know? What is meant by countable? Countable. So it is infinite, right? So that means that would be there exists a way to list out all the real numbers, right? So there exists a way to list out all the real number in 0, 1, 1 by 1. Okay, so there is a 1-to-1 correspondence between 1, 2, 3, 4, 5, 6, the set of that one and this one. So we can list them now 1 by 1. Okay, right? Okay, so let's, and in that case there exists 1. So let's take a look of that listing. Okay, so we can take a look of that listing. listing out the first real number between 0 and 1, and then we may be listing out the second real number between 0 and 1, and then we can be listing out the third real number between 0 and 1, and so on and so forth. Okay. Okay, so imagine, okay, whatever. So let's say this real number R1 is something like 0.5. So it looks like 0.5000. Is that okay? Maybe the second real number, let's say this is like 0. Yeah, whatever we like. So let's say 0.333333. So we will have all threes here. Okay? Maybe the next number is a strange number. That is a real number that is like okay, it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Something like this. Is that okay? So we will have a listing. Okay. And so as such a listing, if there is a one-to-one correspondence, such a listing will never miss any real number between 0 and 1. Okay? Let's list out one more. Okay, so let's say R4. So let's say R4 is equal to what? R4 is equal to 0. Give me a real number. Pi. Okay. Pi without the 3. Okay. So it's like 1, 4, 1, 5, 9, something like this. Is that okay? Yes. So now let us take a look at this listing. We are going to use this listing to create a number and show that number cannot be inside. Inside, yes. So how do we create? Look at the first digit of R1, the second digit of R2, the third digit of R3, the fourth digit of R4, the fifth digit of R5, and so on and so forth. So we just try to get something that is not like this. Okay. So you can create an arbitrary R that doesn't look like this. So there are many ways. So but my way is like this. Let's look at the number. If it is odd, then I will make it even. Replace it by 2. The second digit of this one is odd, so I will replace it by odd. Okay. Whatever. Change it to 60. Okay, because otherwise it was dumb. Okay. So the second digit of R2, this is odd, so let me change it to 2. Okay. The third digit of R3, it is odd again, so I'll make it 2. And then the fourth digit of R4, it turns out that it is even, I'll make it to 1. Is that okay? So I will check. So this R, the digits of R is easy to see. So the kth digit of R looks at the kth digit of RK. Okay? And depending on that, I just make it different. Okay? Now this R is special. This R, so we will have this R cannot be equal to Ri for every I. It is not R1 because the first digit is not the same. It cannot be R2 because the second digit is not the same. Okay? And what's more, this R is one of the number in 0 and 1, right? You get a contradiction. We have found a certain real number inside the set such that it cannot be listed. It contradicts to what we are claiming before. We are assuming that there exists a one-to-one correspondence so that everyone can be listed. Now here, we find someone that cannot be listed. So everyone can be listed and someone cannot be listed. These two things are contradicting each other. So what does that mean? So it means that the original assumption in the proof is wrong. So the real number set, okay, not the real number set, the set 0, 1. All the real numbers between 0, 1 will be uncountable. Is that okay? Is that okay? Okay. Now this is a little bit, it could be confusing, okay? It could be confusing. Yeah. It could be confusing because what happens? A slightly different problem, a slightly different strength will be okay. So it could be confusing. Let's consider a very similar set. Okay, so this is a very similar set, such that it contains strings of this form. So let's take a look of a set. Let me give you a name. Let's call it G. Let's create a set. Let's call G. G contains what? G contains all the strings of 0. Blah 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 of length k. Okay. Such that k is in n, and each question mark is in what? 0 to 9. Okay. So what does that mean? So G contains what? G contains of when k is equal to 1, G contains something like 0.0, 0.1, blah blah blah, up to 0.9. Is that okay? And then when k is equal to 2, then it contains 0.00, 0.01, 0.02, blah blah blah, up to 0.99. Is that okay? K equals to 3, it contains 0.000 up to 0.999. Okay? Okay? And then whatever. So it contains all the possible strings of all the possible lengths. Okay? Okay, but then this is countable. This is countable. They look really close to each other, right? All of them represent strings. That is a number between 0 and 1, right? Right? The only different thing here is that here on this side, each of the number that we are going to write down has one thing in common. They are of finite length. Any number in this set G, it will stop at some point. Is that okay? But that real number set, well, you can have real numbers that it never stops. Okay. So although this set and this set, they are alike, this one is countable, but this one is uncountable. Is that okay? Okay. So I hope you like this. Okay. Now we still have a little bit time. So this is all about countable and uncountable set, and we still have some time. So I want to show there are 2 more results about proof by construction that I have omitted. So the first one is, so proof by construction is that you want to prove something and then you construct something so that you can find out that it's easy to see. So here in this proof by, so here in this uncountable proof, we are actually proving the contradiction part here based on constructing an R. Okay, so this is a kind of construction that we have used here. And then this proof also uses proof by contradiction technique. Otherwise, it is difficult to see. And one more thing here is that this idea of taking the first digit of first, second digit of second, third digit of third, this idea such that we are creating a counterexample that doesn't like each one of them can be used in a lot of different places. And this technique is have a name. It's called diagonalization technique or diagonal technique. So if you have a chance, I will show more results. So a diagonalization technique. Okay. Okay. So now let's take a look of 2 more examples that we can use proof by construction to show. The first one is Pythagoras theorem. So if I have a right-angled triangle, one side of length A, one side of length B, and then the hypotenuse is having length C, and it has this equation: a squared plus b squared is equal to c squared. Okay. So this is the Pythagoras theorem, and actually this is one of the most proven results. So it is a theorem that is reported to have the most number of different proofs. Okay, many people prove this with different ways. Okay, so one way that we can prove is like this. So you can make a shape like this. Okay, and whatever. So that each is A, B, A, B, A, B, A, B. Is that okay? So that this is an angle. This is a right angle triangle. Oh, this is C. C. Is that okay? Now the key point is that if you draw this, if you make an arrangement like this, so the outermost is going to be a square, right? And then we join these points together to get something like this. The inner point is also a square. The reason is that this angle is the same as this angle, right? And then this angle plus this angle is 90 degrees. So this angle plus this angle is 90 degrees. So this has to be a right angle triangle, right angle. So you can prove this again for every angle here. So this is actually a square. Then this result can be proven by just counting the area of this square in two different ways. One is you count everything here is going to be A plus B squared. Is that okay? And then it is going to be equal to the middle square plus 4 little triangle. So we have 4 little triangle. Each of these little triangle has area of AB divided by 2. Is that okay? That's it. So we can prove it. So is that okay? Okay. So similar proof is like this. So a similar proof is just, but you will just consider it as a different proof. You just look at half of it, and this time we are looking at a trapezium rather than a square. But still, you can prove it, okay? Because this is right angle, this is a line, so this is going to be parallel. So this is the trapezium, and then you can count the area in two different ways. So this is another way of getting the result. And if you like, there is another one. So this time it's like this. Yeah, maybe. Let me see. Let me see if I'm going to draw this correctly. So this is going to be does it look like something like this? So this time it's like you have C outside. Yeah, no, C outside, so this is not like that. You have C outside, you have the A here, A here, A here, and then A here. Is that okay? So inside there's a middle part. It's going to be a square of length B minus A. Is that okay? And then you can have something like this. Rather than using A plus B squared, you're using B minus A squared. And then you get another result. Okay? And there are different proofs for this one. Okay? Okay? Good. And then another. Okay. Now there is another interesting question. Okay. This time we want to show that tangent. So tangent theta is a number between 0 and 1, right? So tangent inverse is you get a number between 0 and 1, not 0 and 1, sorry, wrong. So tangent theta is going to be a number between negative infinity to positive infinity, right? So on the other hand, if you get a real number, you can get back to a certain angle by taking the tangent inverse. Is that okay? We want to show that tangent inverse 1/3 plus tangent inverse 1/2. One of the solutions here is equal to pi/4. Of course, there could be a lot of different. So this is an angle, this is an angle. So if you add 360 degrees, then you get the same result, right? So in that sense, So we just want to show that pi over 4 is one possible answer. So how can we show this? So of course we are asking you to not use a calculator. So if you use a calculator, yeah, you can get it, but you will not be convinced. So a proof of this one is like this. It's like the Pythagoras theorem. We are going to show like this. This is 1, this is 2. You get something like this. This is 1. This is 1. This is 2 here. Is that okay? Okay, so we join them together. Join them together. So this is going to be 90 degrees. So each one of them is a. So what is this angle? These two has the same length, right? Right? So this angle is exactly 45 degrees, pi over 4. This is the pi over 4 that we have. And then we add one more line. We add one more line for this one. And what is this angle? This angle, so this is of length 1, right? If you make a parallel line here, this is length 1, this is of length 1. Tangent of this angle is equal to 1 over 3. Is that okay? So this is the tangent inverse of 1 over 3. How about this one? How about this angle? How about this angle? So this angle is the same as this angle, right? So this is tangent inverse of 1 over 2. Is that okay? So by drawing a figure like this, suddenly you get the result. Okay. Now this is hard, but then once you know this, then you can do whatever you like. Okay. So you can create something like this one. Let's say I have a 2, I have a 3, then I have something like this, then I have a 3, I have a 2. Let's say this is 2, this is 3, then you know that this is going to be 90 degrees, so this is going to be pi over 4. So you will then have what? You will then have a tangent inverse of 1 over 5 plus tangent inverse of 2 over 3, that is equal to 5 over 4. Is that okay? So you can create many examples that you like. That's it, right? This time it is like 1 over 5, and then this angle is 2 over 3. So, okay? Yeah, hope you like it. So, okay, so on Thursday, we will talk about something new. We will look at number theory. Okay, we will talk about some introduction to number theory. So we will not go into very much detail. But a lot of results you have already known. Like each integer, there is a unique way to factorize it into primes. So unique prime factorization. And then some maybe you are not familiar. Like, so for the greatest common divisor, I have two numbers. Let's say 3 and 5. The greatest common divisor is going to be 1, right? You can always write down 1 as an integral linear combination of 3 and 5. So what does that mean? So 5 and 3, right? So 2 times 5 minus 3 times 3 is equal to 1. Okay? So any greatest common divisor, this is going to be a small number. You can always express it as what? A linear combination or integer linear combination of the two numbers that we are talking about. So this you may not know, but this is going to be something. Okay, that's it for today. Thanks a lot.